we started talking about parent functions. We then started talking about some transformations. We talked about translation, whether it's horizontal or vertical. And then we ended last class with talking about reflection, whether it's around the x-axis or on the y-axis, right? Now, it will be on the test, I will give you a problem and then ask you to name the transformations, right, that have been applied to that function. And when I ask you for that, like there are a couple of examples of that in the homework. When I ask you for that, I am looking for technical language, right? So not flipped horizontally, no, reflected around the x-axis, okay? Reflected around the y-axis and so on. Okay, so when you're doing the homework, make sure you're using the technical language for that. And then if you have questions tomorrow, we can go over those. All right, so today we're going to talk about dilations, whether vertical or horizontal dilations. So if we start talking about first a vertical dilation, what this is the following. Suppose you have your function f of x is equal to x squared, and we know that that's a parabola, okay? Now, suppose my parabola was made of like a rubber band type of material or something, right? And now suppose I tied a string to the edges of this, like this, right? Like that. And now suppose I like held on to that and I just moved my hand upwards. What would happen to the parabola? It would stretch vertically, right? And it would look like it's getting narrower, right? But really what's happening is the points are being stretched. So this point here, right, it's not just getting narrower like this. This point here is moving up to that, right? That's what's happening, all right? That's a vertical dilation. So, in other words, suppose this was g of x equals, I don't know, 5x squared, right? Or let's make it smaller. Let's make it like 3x squared, okay? What would happen is that, so in the parabola, I know that if I move over one space, I go up 1 squared, right? But now this not only brings it up 1 squared, it then multiplies it by 3. So instead of going up 1, I now go up 1 times 3 units. Okay? Similarly, if I go over 2 units, let's say, I should have gone up how much? 4, but now I go up 12, 4 times 3, right? That's a vertical dilation. It moves everything up quicker. That's what it is. If I were to do the same thing, but now instead of pulling up on the string, if I were to squish down, what would happen? It would look like the parabola would bulge out. But really what's happening is I'm pushing down on each of those points, right? So now, what would that look like? That would look like if I have g of x equal to 1/2 x squared. Now, if I had gone over 2 spaces, instead of going up 4, how much am I going to go up now? Half the amount, 2. Okay? So now, there are 2 situations then. Both of these are called dilations. I know it's kind of like counterintuitive. But I have one situation where it's being expanded vertically. That happens when this factor a is greater than 1. Okay? That's when that happens, when a is greater than 1. Or you have a compression, and that happens when a is not less than 1, because, then we take negatives and stuff as well. When a is between 0 and 1. Okay? So, when it's like a half and so on and so forth. All right? Okay. Now, horizontal dilations. Horizontal dilations are when you now either compress horizontally, you either squish the parabola or you expand it like this. Okay? So, how that works is this one is a little more difficult to visualize. Yeah.
What's the difference between expanding vertically and
That's what I'm going to talk about right now. So, suppose here I have g of x is equal to 3x squared, right? Do you see where the 3 is? It's inside. So, if I were to go over 1 unit, what this function does, its order of operations. First, it multiplies it by 3, so it's like you went over 3 units. Then it squares, so it goes up 9. You see that? Let's think about that one more time. If I go over 2 units, what it does is, first it multiplies it by 3, so it's like I went over 6 units, and then it squares that, so I go up 36. You see that? That's what that does. So for the same amount of time, when x equals 2, instead of me being up here, I'll now be further up. Okay? So that's what it does. It doesn't like move it out, it just moves it up. All right? Question?
Yeah. So if you have
the opposite, if so that happens, so it's compressed horizontally. Ooh, mixed colors there. It's compressed horizontally if a is greater than 1, and then it's expanded horizontally if a is between 0 and 1. What makes it sort of difficult is so when you look at something, the vertical dilation and the horizontal dilation may seem like they're the same, right? Because in both cases, right, you're either making it narrower or wider. But just know that internally, backstage, it's a different process. So how about when I ask you, I'm okay if I don't need you to know expanded vertically or compressed vertically or horizontally. If you just know that there is a vertical dilation or a horizontal dilation, that's good enough. Okay? So, if your function is f of x is equal to 3 root x, right? Just say vertical dilation. If your function is, I don't know, absolute value of 5x, that would be a horizontal dilation, right? Because one is inside, one is outside. Okay? Does that make sense? Okay. Yeah, if it was, let's say, g of x equals 1/3 x squared, right? So now if you go over 1, it scales it down to 1/3 and squares that, and it goes up 1/9 instead of 1. Yeah.
But anything that absolute.
Okay. So the thing with horizontal, with the absolute value is there is really no difference. It looks the same. That's the equation for horizontal dilation, but when you graph it, it'll look the same.
Oh, okay.
Yeah, because it's linear. Yeah.
What should we say?
It's a horizontal dilation because the 5 is inside. Okay? So if it was f of x is equal to 5x, it's a vertical dilation.
Oh, okay.
Yes. Huh? Yes. 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 Okay. All right. So here it says identify the parent function, then describe how they're related. So what's the parent function here? Right. F of x is just absolute value of x. And now, how are they related? So g of x has a what? There is a reflection around the x-axis, and there's a horizontal dilation. Okay? All right. So to graph this, it says to graph f and g on the same axes. I'm just going to graph g of x for now. So this is going to be negative absolute value of 4 of x, right? So my vertex is still there. And now if I go over 1, I'm going to go down 4. And it's symmetric. And that's all I need. Right? Look, lots of different ways to graph this. If you want to pick points in your mind and do it, like it's fine. Like to me, it's the same. What I care about is that you are able to graph this, because come next year in calculus, if I give you this and then some other function like x squared minus 5, I need you to know where they intersect, how they look, which one is higher, which one is lower, and so on, right? So I will give you all the tools you want. If you want to plug in points, just figure out the quickest way for you to graph these things. Now, if I ask you for some coordinate points, you can give me some coordinate points, right? Zoe, question.
I'm curious how, like, what did you mean with Lee's seed and know that is graph?
That was what?
That was how you have to graph it.
Because it's an absolute value, it's a v, right? And because there is a negative out front, that's a vertical that's a reflection. It means instead of opening up, it's going to open downwards. Okay?
Do you know that you can plug in anything for x?
Right. Yeah. So imagine, so even if you didn't see it, right? You know that when x is 0, y is 0. Oh, this is 0, 0. What did I do? Right? You know that when x is 1, y is negative 4. And I know that this is an absolute value, so it has to be like a v. So what I tell my students all the time is, absolute value, right, has a graph like v for value. It looks like a v, right? The square root graph, right? Look at what the graph looks like. It looks like a radical symbol, right? So just little things. Okay. Oh my gosh. Okay, so take a look at this next one. I have 1 over 4x squared. So what's the parent function? X squared. You mean f of x equals x squared? Yes. So what are some of the what's the transformation that's happening here? This is a vertical dilation, yeah.
But it's being compressed vertically.
Right. It's a vertical compression, but it's fine. If you just say vertical dilation, I'm cool with that. Okay? You don't have to tell me compression or expansion. Okay. So, this is what shape? Parabola. Where is the vertex of this parabola? 0, 0. So now you need to graph this thing. What if your heart is telling you to pick points? Okay, so pick points. All right? Can you pick a point? This is a simple enough parabola. We're like, okay, x is 1, y is 1/4. X is 2, y is 1. You can do that. Okay? And then you mirror on the other side. Or instead of going over, okay, so if I go over 1, instead of going up 1, it's 1/4. If I go over 2, instead of going up 4, it's 1/4 of that, 1. And then I mirror them on the other side. How I got those points makes no difference to me. This is going to be on the no calculator section. It's you and you who are graphing this, right? There is not much work to show me, okay? There is not much work to show me. So I'm not going to, go around saying, don't you dare show me a chart or show me a chart or just graph it. The point for me is you know how this thing looks. So, and then if you wanted to put in some points, you can put in some points. Okay, question.
Yeah, isn't vertical dilation separate to the number in the x?
So it is, right? Because what's being squared here? Is it the 1/4, the x, or both? Yeah? Okay. All right. So next one. Okay, so the next one is the piecewise, right? This is the ultimate test right now. All right, can we do a test? Can we do a piecewise? All right, so let's get started with this. Okay, I have a piecewise function. How many regions? 3 regions. I said in the very beginning that we'll draw our little helpful lines for the boundaries. And then I said, once we get used to this, we're not going to do them anymore. So as promised, I'm not going to draw those lines anymore. And let's see how we can do without it, okay? Now, I have one region for x is less than 0, all right? Then I have region 2. Then I have region 3. What did I say was the most important thing? The first thing you do when you're going to graph one of them? Plot which point? The ones that are on the boundaries, right? So for region 1, what x value am I going to plug into this? 0, right? So you take 0 and you plug it into here and you get 3. So here, at 3, I put in an open circle. Okay, now, what's being graphed there? It's negative x plus 3. It's a linear function with a slope of -1. It's a linear function with a slope of -1. So now it's up to you what you want to do. Do you want to pick another point like -1 and plug it in there and get 4? You can do that, okay? Here, when x is -1, y is 4, right? Is that true? So y is negative x plus 3. Y of -1 is -1 plus 3, 4. Or if you just knew that, it's supposed to be like down 1 over 1 and graph a line with a slope of -1, that works too. Okay, so we did that one. Region 2, I'm going to plug 0 into x, right? And get what? 0, closed circle. I'm going to plug 3 into x and get 6. So when x is 3, y is 6, that's an open circle. That's a linear function, so I just have to connect those points with a straight line. Region 3, first I plug 3 into here, and I get 2, right? When x is 3, y is 2, closed circle. And now that is supposed to look like a square root. What other function can I plug in there what other number can I plug in there so I get a nice little curve? 8. When x is 8, y is 3. Okay? There we go. Isn't that cute? You don't need them. You can put them. It's not a deal breaker either way. Okay? Cool. All right. Oh, I like this one. Okay. X plus 2, absolute value of x plus 2, absolute value of x minus 2, and so on. All right. So, first one, okay? Here, first one. At x equals 0, what is this? 2, right? And it's an open circle. But now, this is an absolute value of x plus 2, right? What does that look like? Where is the vertex? To the left at -2, right? So that's what it would have looked like. Now, I'm only graphing this much of it. Okay? So, when x is -2, it's 0. And then it goes up this way. So it looks like this. Right? So that's what that looks like. So that's an absolute value of x minus 2, but only part of it is graphed. Okay, then here, number 2. Okay. That's from 0 to 2, right? Okay. Okay. If this was not a piecewise function, what would absolute value of x minus 2 have looked like? Where is the vertex? At -2, and then what would it have looked like? Like this? Is that right? Right? But now I'm only gonna I only need from 0 to 2, so I don't need everything else, right? So why am I doing this? Because in your mind, you need to be able to visualize what it was and what it is now. Okay, so first we plug in x is 0, and we get that y is -2 with a closed circle. When x is 2, right, we get 0 but open circle. And that's what that looks like. And then finally, the last one is a square root again. So when x is 2, what's the y value?
4.
4. 1, 2, 3, 4, open circle. And then what else can I plug in here? 7, and I get 5. Right? Like that. Okay? Questions? Questions? No questions? That's either a very good or a very bad thing when there are no questions. Is it a good thing? Okay. All right. Now, what happens when the absolute values come in? It's possible to put an entire function in an absolute value, right? What an absolute value does is it makes all of the y values positive, all right? So, look at this one. If I have f of x equals x squared, that's what, no, not x squared, x squared minus 2, that's what it looks like, right? Now, if I take that entire function and put it in absolute value, you know what it does? It takes whatever was negative and reflects it up like this. Just reflects. Okay? Isn't that cool? That is so cool. Okay. Yeah. Did I talk about that yesterday? I did. Go back to the notes from yesterday. Okay. Now, and I did talk about it here in H period, so it's like the same exact thing yesterday. Okay. So, now, what if, so this is, let's say, y equals x minus 2 squared, right? Now, what if I were to graph absolute value of x minus 2 squared? Just the x is in absolute values, right? So now what it does is the following. This says, you know what? Whatever negative x values there are, like you can no longer have negative x values. So it takes the negative x values, makes them positive, and gives it that y value. Okay? Let's think about that. So let's think about that. Suppose this is x equals 2. Okay? Where is x equals negative 2? Right here. It was supposed to have this y value. But guess what this function does? You put in a negative 2. It makes it positive 2. And what was the value for positive 2? 0. So now it gives it that value. Let's think about that one more time. You give it x equals negative 2. It says, no, x can't be negative 2. I'm going to change it to positive 2. What is f of positive 2? 0. So at negative 2, it gives it the same value as what it was for positive 2. Okay? So what you have to think about is this. When you have just the absolute values, it takes away anything in the negative x's, just takes it away. What have you got left? This much, right? It takes that and then multiplies it one more time. Okay, so it just takes that and mirrors it over. All right, we're going to practice a little bit. And you know what? I should have given like more a second graph here, but I didn't. But it's okay. We'll make do with this one. And I'm actually gonna give you another function here, a simpler function. Why don't we do I'm gonna give you a function in vertex form. Let's do x minus 1 squared minus 2. So I want to graph f of x, absolute value f of x, and f of absolute value of x. So let's first graph f of x. What's the vertex here? 1 and negative 2. So 1 and negative 2. And then if I go over 1, I go up 1. Mirror it on that side. If I go over 2, I go up 4. 1, 2, 3, 4. Mirror it on that side. Okay. Questions? Do you guys have questions? Stop me if you do. Huh? Okay. Okay. So hey, look. So this is the axis of symmetry, right? At x equals 1. What if you're like, you know what? I'm just going to plug in x equals 2 in here. When you're given vertex form, it's the best situation to plug in numbers. If you plug in x equals 2, you get 1 minus 2, negative 1. Negative 1. If you plug in x equals 3, 3 minus 1 is 2, squared is 4, minus 2 is 2. That works as well. Okay, so that's f of x. Now, Can I graph absolute value of x? What's absolute value of x gonna do? Yeah, take that and reflect it. So whatever is negative, which is this, right? That's the negative part. It's gonna reflect it up like this, right? So it's going to look like this. Let me erase this. All right, so that red is the absolute value of x. Okay, so for this one, I'm actually going to make another coordinate axis here. Why can't I make that straight? Okay, so now here's what we're going to do. For this one, you take everything on the positive x-axis, right? Everything in the positive x-axis, that is this. Is that right? And then you mirror it one more time so it looks like that. Okay? So here, from here to here, just all of the ones where x is positive. So you take the ones where x is positive and then you mirror the same points on the other side. You just do it again. Just copy it over. Yeah. Oh, yes. Yes. For the one on the left, it would look like g of x is absolute value of x minus 1 squared minus 2. And then h of x is just the x in absolute values. Yeah. I would give you separate ones. I would give you separate coordinate grids. Okay. This homework will be due next time.